Hello everyone, Assalamu alaikum. Welcome back to our VLSI system series. In this video, we are diving into the core technology behind modern integrated circuits, that is CMOS logic. If you're ready to explore how transistors work together to form the foundation of all digital electronics, then you're in the right place. Now let's start with the basics. Modern electronic chips are built mostly on silicon substrates. Silicon, a group 4 semiconducting material, forms the foundation of all our VLSI systems. By adding dopants to silicon, we can control its conductivity, enabling the creation of complex circuits. The next key concept is the PN junction, the building block of semiconductor devices. This leads us to two main types of transistors: bipolar junction transistors, which we call as BJTs, and metal oxide semiconductor field effect transistors, which we call as MOSFETs. So MOSFETs are especially crucial in VLSI because of their ability to be integrated in high numbers with low power consumption. Let's try to understand the basic MOS structure. MOS transistors have four terminals: gate, source, drain, and body. The voltage applied to the gate controls the current flow between the source and the drain. In digital circuits, these MOS transistors acts as switches, which is fundamental to how logic gates operate. Now let's break it down further with NMOS and PMOS transistors. NMOS transistors conduct when the gate voltage is high, while the PMOS transistors conduct when the gate voltage is low. By combining these two, we can create the fundamental building blocks of digital logic, like the CMOS inverter. Now let's establish some ground rules for voltages and logic levels. So we have to represent logic level 0 and logic level 1 with some appropriate voltage levels. So for logic level 0, we would be calling something like ground or VSS. That will be representing our logic level 0. And for logic level 1, we can say that our power supply or VDD, that represents our logic level 1. Now these voltage levels, in particular VDD or supply voltage levels, have been decreasing substantially throughout the years. Starting with the 1980s with 5 volts, this voltage level has been decreased substantially to even lower values than 1 volts. With this in mind, let's go to our main topic, the CMOS inverter, the first digital circuit that we will study. Now, the CMOS inverter is one of the most basic yet essential components in digital circuits. It consists of one NMOS and one PMOS transistor. So the theory is when the input is high, the NMOS turns on, pulling the output low. Conversely, when the input is low, the PMOS turns on and pulling the output high. This simple configuration is what allows digital circuits to perform logic operations. Let's try to understand the structure of this CMOS inverter, how this is connected. So as you can see, PMOS is in the upper part of the circuit and NMOS is in the lower part of the circuit. For MOSFET, there are three terminals that need to be connected, that is drain, source, and gate. Let's break it down further. As you can see, the gates of both PMOS and NMOS transistors are tied together. That leads to the input. So the input comes from here. And as far as the output part is concerned, both the devices' drain terminals are connected together. That leads to the output, logic Y. For PMOS, the source is connected to VDD, and for NMOS, the source is connected to ground. Hence, this gives us complementary output. Now let's try to understand the operation of this inverter, how this works. When we supply the input terminal of this inverter with a logic level of 0, what happens is that for PMOS transistor, the gate is getting a 0 logic, so it will be turned on. And for NMOS transistor, because the gate is getting a 0 logic, so it will be turned off. So in that way, only one part is connected to either supply or ground. So in this case, because of 0 logic, the PMOS transistor turns on and this pulls the output logic to 1. Alternatively, When we supply input A with one logic, so PMOS transistor will be turned off, so this path will be open, and NMOS transistor will be turned on, pulling our output to the low logic of 0. So this is how CMOS inverter works. Now building on the inverter, we can create more complex gates like NAND and NOR gate, which are the building blocks of all the digital systems. CMOS technology ensures that these gates operate with low power consumption, making it ideal for high density VLSI designs. Let's try to understand the operation of a basic NAND gate. As we know that output of NAND gate is only 0 if both the inputs are 1. So the configuration remains the same. Configuration for all the CMOS logic gates remain the same. You will always have a pull down network at the bottom, and by pull down network I mean collection of NMOS transistors, and the pull up network will always be at the top connected with the supply VDD, and by pull up network I mean the collection of PMOS transistors. So there will be no NMOS transistors in the pull up network, and there will be no PMOS transistors in the pull down network. By pull up, this terminology pull up comes from the fact that when this part is turned on, when the upper part is turned on, then this output is pulled up or pulled high. And alternatively, when the lower part is turned on, or when the pull down network is turned on, then the output will also be pulled down. And there is only one thing happening at a time. Either the output is pulled up or pulled down. Now let's try to understand the operation of CMOS NAND gate. Before diving into the operation, let's talk a little bit about the configuration, how this gate is connected. So as you can see in the pull down network, in the NMOS network, both the transistors are connected in series fashion, and in the PMOS network or pull up network, both the transistors are connected in parallel fashion. By parallel, I mean both the drains are connected and both the sources are connected. In the same way, by series, what I mean is that drain of one transistor will be connected to the source of the other transistors. In this way, as you can see, or as you know, that when the circuit is connected in series, if one component is open, then the whole path will be open, and there will be no path for current to flow. So in this case, when either one of the transistor is turned off or the switch is turned off, then the whole network will be turned on off. And conversely, for parallel circuits, the current will flow even if only one of the transistors is turned on. So in this case, if either this transistor or this transistor is turned on, then the circuit will be connected to the supply and output will be pulled high. Let's try to understand the operation of this CMOS NAND gate. If both the inputs are 0, let's consider one by one. If the input A is 0, then the corresponding transistor, NMOS transistor, will be turned off, and the corresponding PMOS transistor will be turned on. And as I have just told you, because this is a series network, if even one of the transistor is turned off, then this whole circuit is open, this whole path is open, so this network will be open. And alternatively, if this is turned on, then this supply path is connected, hence the output will be turned on or pulled high. And the same scenario goes for if A is equal to 0 and B is equal to 0, if A is equal to 0, B is equal to 1, and if A is equal to 1 and B is equal to 0. Now what happens if both the inputs are 1? Then both of these transistors are turned on, so the path is completed, and both of these transistors in the upper network are turned off, so this whole network will be turned off and this whole network is turned on. And because this whole network is turned on, so the path of conduction is on, and the current will flow towards the output. So this time the output is pulled low because of this connection to the ground. So this is how the CMOS NAND gate operates. Now let's move our attention to CMOS NOR gate. And we know that for NOR gate, if both the inputs are 0, then only the output is 1, and for the output for all the other combinations are 0. Let's see how this circuit is connected. So as you can see in the pull down network, both the transistors are connected in parallel, and for pull up network, both the transistors are connected in series. As you can recall, this is reverse of what was happening in the NAND gate. So the operation will also be reverse. So if we provide input logic 0 to both the transistors, let's consider the first case. If we provide input logic of 0 to both the inputs A and B, then what happens to the pull-up network? Both the transistors, PMOS transistors, will be turned on, and this conduction path will be closed. And because of this, this output will be pulled high. And alternatively, for A and B both being 0, both of these NMOS transistors will be turned off. So there is no conduction path here. Then comes the turn if A is equal to 0 and B is equal to 1. So if A is equal to 0, this transistor will be turned on, but because of B being 1, this transistor will be turned off. So this whole network is turned off, and because this one transistor connecting to B is turned on, so this output will be pulled low again. Similar is the case if A is equal to 1 and B is equal to 0. If A is equal to 1, then this upper transistor is turned off and this lower transistor, PMOS transistor, is turned on. But this, because this upper transistor that is connected to A input is open, so there is no conduction path here. So in the lower network, what happens is that this transistor, NMOS transistor connected to the input A, is turned on, and because of that there is a conduction path from this ground to output. So the output will be pulled low. So up to now we have seen the three basic logic gates, the working of three basic logic gates: the inverter or NOT gate, the NAND gate, and the NOR gate. So if you observe closely, when we had only one input, we had the basic inverter gate, and for inverter there were only two transistors. So for one input there are two transistors that are connected in complementary fashion, one for PMOS and one for NMOS. In the same way, if we increase our inputs, the number of transistors will also increase accordingly. We saw in the NAND and NOR gate case. For two input NAND gate or NOR gate, we had two PMOS transistors and two NMOS transistors. They were either connected in series or in parallel, but they were connected in the complementary fashion. Hence the name complementary MOS transistors or complementary MOS circuits. In a similar way, if you keep on increasing your number of inputs, like you can see here, this is the 3-input NAND gate, the number of transistors will also increase with the number of inputs. So you have 3 inputs, 1 input for each transistor. So this is the basic order of CMOS networks or CMOS circuits, that if you increase the number of inputs, then your corresponding number of transistors will also increase. For this case, for this 3-input NAND gate, you have 3 PMOS transistors that are connected in parallel and 3 NMOS transistors that are connected in series. And the operation of this is the same as we have just studied. CMOS gates are designed to consume power only when switching states, making them highly efficient. They also retain their previous state due to the capacitance at their nodes, which is sometimes used for dynamic storage. Understanding CMOS logic is crucial for anyone looking to dive deeper into VLSI design. In our next video, we will explore how these basic building blocks are used to create more complex circuits and systems. Don't forget to like, subscribe, and hit the bell icon to stay updated on our series. Thanks for watching.